Welcome to the first of our webinar series related to describing a site. Today we're going to talk about chemical fate and transport, and what I'm going to try to do is to minimize the technical jargon if possible, and also I think I've eliminated all equations. So I'm Mike Sklash, and I'm going to talk about chemical fate and transport today. Just a little bit of background on me. I'm a geological engineer and also have a master's and PhD in earth sciences from the University of Waterloo, where I studied groundwater. I was a professor doing research and teaching for about 15 years and still do it occasionally. Since '92, I've been senior hydrogeologist at Dragon, and I do generally expert work, meaning litigation support and larger projects, and I do that in both Canada and the United States. This is a three-part webinar series that we're going to talk about to help you to optimize your time and or money if there's a groundwater contamination issue, to try to get you to understand so you don't have to repeatedly do these things over and over. So today we're going to talk about chemical fate and transport. Next week we're going to talk about conceptual models, and 2 weeks after that we're going to talk about groundwater models. So if you have any questions today during the webinar, you can contact Alan Hahn at the email given, ahahn@dragon.com. If we have time at the end and you have questions, we can discuss those. Otherwise, I'll be happy to answer questions if you email me at msklash@dragon.com. So why discuss chemical fate and transport? Well, number one reason is many remediations take too long and are too costly. And the reason for this is because the site is not well understood. And we're going to talk about that in the physical sense next week. Today we're talking about chemical fate and transport. Also, to help you determine if you've contributed to a groundwater contamination plume. Often people are brought into lawsuits and may not have contributed. We're going to talk about understanding chemical fate and transport so you can determine where you stand on that issue. So today we're going to talk about how does a release become a plume, what controls the rate of plume movement, how do chemicals behave. I'm going to do 4 what I call mini case studies, describe case studies that we've worked on, some litigation, some not, that demonstrate some of the theoretical things that we're going to talk about at the beginning of the talk. So this is a release. This site was an instance in 2005 where a tanker truck carrying gasoline and a car collided. The tanker truck tipped over the side of the road, spilled thousands of gallons of gasoline into this sandy soil. What you're seeing at the bottom of the picture is actually the water table. So the chemical got into the water table almost immediately. So what happens once you get that release? It's easy for us to visualize things we can see, and we can see smoke plumes taking shape like we can see in this picture out my backyard. However, groundwater plumes are more difficult to visualize because everything's underground. But they look kind of like what you see in that picture. Talk about the plume experiment that Jim Barker and his associates did in 1987, where they released a known amount of a chemical at a starting point and watched it migrate in the groundwater flow. So I'm just assuming north and east here. The release at the first day, and we're assuming the mass is 1. All the mass is at the release point, and we're going to assume it's a conservative chemical. And what that means is the concentration only changes by mixing with a water which has a different concentration. So after a certain number of days, the mass is moved. It's still total mass of 1 because it's a conservative chemical. The release is turned in from a point release into a elongated release in the direction of groundwater flow. And although I'm showing the mass here as kind of a solid, it's really a concentration gradient across this oval because it's affected differently at different parts of the mass. We'll talk about that in a couple minutes. After further time, lower concentrations but the same mass, and 2 years or so on, again the same mass, lower concentration. It's spread out in the direction of groundwater flow and across the direction of groundwater flow. So in summary, when you have a release into the groundwater, the plume moves from the source in the groundwater flow direction. The plume elongates in the groundwater flow direction. It also widens and becomes deeper, but those are much smaller changes than in the groundwater flow direction. If it's a conservative chemical, the mass remains the same, and this is kind of highlighting it, day 1, after a bit of time, after more time. So these aren't occurring at the same time, they're at different times. So the mass remains the same at different times. The concentration of the plume decreases as the plume grows, but the mass remains the same. So how are these two different? The smoke coming out of the stack and a conservative tracer released. There's a continuous source here. So we could have another type of test where we have a continuous source and our plume would look like this. So it's important to understand whether you have a continuous release or not into the groundwater. So once you have your release, why does the plume spread? Well, the first major reason is advection. That means it's moved along by groundwater, which moves. Now, unfortunately, we can't see that very well, so I've got a picture of a nice mountain stream, which basically is, kind of the same thing, advection, it's moving. In groundwater, we have another factor of the plume movement called hydrodynamic dispersion, and that means transport by mixing. So there's two components of that. There's the mechanical mixing by movement, and I like to show a downtown area with roads to give you an idea of what a porous medium, what the groundwater would go through. It's got pathways or roads it can follow, and there's different pathways, different sizes, and so on to get from point A to point B if the groundwater is moving this way. The second way we have mixing is by concentration gradients, and that's called diffusion. That's important but often ignored method of moving chemicals. So in mechanical mixing, as the groundwater is flowing, let's assume that these are two sand grains, and they're separated, and that separation is called a pore. The water moves through the pore. The greatest velocity will be in the center of the pore, and the lowest velocity will be at the grain boundaries where there's a lot of friction, relatively a lot of friction. So if you have a chemical that is in the center of the pore, it will move faster and further than a chemical that's at the edge of the pore. We can also have velocity variations because the pores are different sizes. Larger pore will have a larger velocity, smaller pore, smaller velocity, and therefore chemical will move less in a small pore than it will in a large pore. And then the third factor here is tortuosity, that we don't have straight tubes that the groundwater flows through. We're moving through a tortuous path around grains, and that mixes up the water with the chemical. So that was looking at grain size, but at a larger scale, a macro geology scale, this is a limestone with pores in it where water can flow. So you can see that the water can move through these pores and that will tend to spread a chemical. Or if we look at this roadside cut, we can see water moving down the slope at 3 spots. So the water has pathways that it can follow that helps to spread the plume. Diffusion is chemical movement by the concentration gradient, as I mentioned. It's governed by what's called Fick's law, and basically this is chemicals moving from areas of high concentration to areas of low concentration where the groundwater velocity, the advection, is negligible or absent. So the best way of conceptualizing this is thinking about a tea bag in a cup of hot water. If you watch it, you'll see the color of the tea move outward from the tea bag, and there's no advection, there's no movement of the water. This is very important in soils that don't transmit water very quickly, like this clayey soil here. So if you have a release into, say, a soil, and it's up against this very massive clay soil, the chemicals will migrate into the clay soil slowly because of the concentration gradients. So this is kind of a similar situation. This is a site where we were looking at manure ponds, and it's got clayey soils here, and this is where you would think that diffusion would be important, but you see these wet spots in the bottom. This clay soil is fractured and water moves up. So if there's contamination that is in the groundwater, it will preferentially move by advection through the fractures, but at the same time will be diffusing into the clay, the massive part of the clay. So if you go in here after, say, there's a contamination release, try to clean it up, many times the cleanup effort is focused on getting the easily obtainable water, like the water in the fractures, but not the contaminants that are in the clayey soil, the matrix. And after you finish your cleanup, often what happens is the chemicals that are trapped in the clayey soils come out into the water, and you get a recontamination. So advection and mechanical mixing dominate in permeable soils like sand and gravel, and they result in large groundwater plumes. Diffusion dominates in low permeability soils, and we'll talk about this in a couple of minutes, like clay, and they result in a halo of chemicals. They don't go very far, but you can move quite a bit of chemical. So what controls the rate of a plume movement? We talked about advection and mechanical mixing a bit. We'll look at that in a little more detail. Diffusion also we looked at, and we're going to look at a factor called retardation. So advection, or groundwater velocity, is controlled or described by Darcy's law. And Darcy's law is made up of 3 factors. The groundwater velocity, V, increases with hydraulic conductivity, which I'll talk about in a minute. It increases with hydraulic gradient, which I'll talk about in a minute, and it decreases with an increasing porosity. So the more porosity, the lower the velocity. So we're going to talk about those briefly. So hydraulic conductivity describes how easily water moves through a soil or a rock. A more common term that you might know of is permeability. Hydraulic conductivity is a better term because it takes into account the fluid properties where permeability doesn't. So on the left we see a sandy soil that's impacted by gasoline. On the right we see a metamorphic rock called gneiss. And the hydraulic conductivity between various geologic materials has a huge variation. 13 orders of magnitude, that's 1 with 13 zeros behind it, is the range from the most highest hydraulic conductivity to the lowest. So this is an important factor to know. The hydraulic gradient is basically the slope of the groundwater surface and the subsurface. And we determine that by measuring groundwater elevations like these guys are doing in a well. And think of the hydraulic gradient as being like the slope on a hill. The higher the slope, the quicker you move down it. And that's the same thing with groundwater, all other things being equal. And then porosity is the pore space. And it can be primary pore space like we see on the left in this sand, or what we call secondary pore space. It forms afterwards in a rock. In this case, it's a fossil that has been dissolved out of a limestone. But the greater the porosity, the lower the velocity. In terms of mechanical mixing, an important property that we talk about is dispersivity. And it's an intrinsic property of the geology which affects how something will spread out. And in terms of, say, a soil, it depends on things like the grain size distribution, or are they all the same size or not, and so on. And so as we have moving groundwater, there's this intrinsic property of the geology called dispersivity, and we get dispersion of the chemical. And Gelhar had a number of papers where he showed that, or they showed that the bigger the area you look at, the more something will disperse. And we can kind of see that in the next slide. I've got a little piece of sandstone. The dispersivity that would happen, or the likelihood we get a lot of spreading, is limited because it's a small sample. But out here in the Grand Canyon, where we have water that might move through several layers on a bigger scale, we'll get more spreading, which seems kind of reasonable. We talked about diffusion before, concentration gradients again. Groundwater with chemicals could move through easy flow paths. At the same time, chemicals are moving by diffusion into the less easy flow paths, into the matrix here in this rock. This is a limestone, and will eventually come out. So retardation is a condition where certain chemicals move slower than the groundwater. And organic chemicals, for example, will move slower than groundwater, and each chemical will be different. So what controls retardation is, number one, the affinity of chemical for a soil versus being in the water. Some chemicals won't move very much at all in a soil situation. For example, PCB tends to stick to the soil, whereas something like MTBE, which is a gasoline additive, tends not to be stuck to the soil very much. And the other factor is the organic carbon content of the soil. As that increases, it will tend to slow down the movement of chemicals. So this is a little chart that I made that is a hypothetical situation which shows the relative retarded velocities of gasoline components. So it's showing the distance traveled by time, and distance divided by time is velocity. So the faster chemicals will move further in the same amount of time. So this is water, the top line, dashed line. So that would be the groundwater velocity in this hypothetical case. These other chemicals are components that come out of gasoline: benzene, toluene, ethylbenzene, xylene. MTBE was an additive in the 90s. And we can see that MTBE, this color, travels almost as quickly as groundwater. Benzene, maybe 60% of that velocity. Toluene less. Ethylbenzene and xylene are about 15% or 20% of the velocity of the water. So you can have one release of gasoline, but the chemicals that come out of that can travel at different velocities. Therefore, when you're trying to characterize this site, which we'll talk about next week, you want to make sure that you understand that different chemicals move at different rates. How do chemicals behave in groundwater, and this is really going to be a quick overview. We can have chemicals that are conservative or not, miscible or not, stable or not, and I'll talk about these a little bit. So when we looked at the initial few slides, we were talking about a conservative chemical. That conservative chemical changes concentration only by mixing with groundwater of a different concentration. And remember, we had the release time 0, time 1, time 2, time 3. We can see a plume moving through the groundwater flow system. If it's not conservative, say if it's like a gasoline components that biodegrade, or radiogenic isotope that degrades with time, then what you would see is the concentration, the mass would be reduced with time. Even though the plume might get bigger, the overall mass decreases until it's gone. Whereas in conservative, the mass is always the same. It's just spread out. Miscible or not means, does it mix with water very well or not? Here we've got the classic oil and water do not mix case, and we can see that in real life. This is gasoline, which tends not to be miscible in water, and we're taking this out of a well, so on top of the groundwater we have a considerable thickness of gasoline. So there are two types of chemicals, two groups that we often deal with in the immiscible, the ones that don't mix very well. The first one, L-napple, light non-aqueous phase liquid. This is a chemical that doesn't like mixing with water and is less dense than water. An example would be gasoline or any kind of fuel which is lighter than water. When it's released, if there's enough, it will migrate down to the water table where there's groundwater and then accumulate there, and then gradually chemicals will dissolve out of that gasoline. So that's a light non-aqueous phase liquid. We also often deal with D-napples, dense non-aqueous phase liquids, things like TCE trichloroethylene or perchloroethylene or carbon tetrachloride. These are chemicals that are often used for cleaning metals, for example. PCE is used in dry cleaning. These chemicals don't like to mix with water. They're heavier than water or denser than water. So if enough is released, they will actually migrate through the saturated zone and accumulate on a low permeability layer. So it's important to know what kind of chemical you're dealing with, and we'll show you why in a couple of minutes. Stable or not, something that's stable might be something like chloride that's released like from road salt or from a landfill, and those concentrations only change, by mixing with water with different concentrations. Something that we often deal with is the weathering of fuels, things like gasoline or diesel, and this is a page out of Jim Dragon's book on gasoline, and these graphs here are GCMS graphs, which basically you can use to interpret the concentration of various chemicals by when they come out in the GC reading. And this is what an unweathered gasoline would look like. Gasoline that is evaporated will tend to lose these early components, and the height of the late components will become lower. And this is what diesel might do when it's evaporated. So if you get a release of, say, gasoline, if it's near the Earth's surface or the ground surface, it will evaporate. If it's deep, like if it leaks from the bottom of a tank, you may not see this factor. Another factor that contributes to weathering is water washing. How soluble are the components? And another one is microbial degradation. Are the conditions ripe for biodegradation? So you need to understand that when you have a release. So I'm going to look at some mini case studies. that address a number of these things that we've talked about with chemical fate and transport. This is a project that we're working on right now in Salina, Kansas. Salina is the geographic center of the United States, and then in the 50s and 60s, this was very important as a strategic air command base. This was a place where the Russians couldn't reach with their bombers. So they had B-52 bombers and other bombers and all sorts of things where they used trichloroethylene, and they used trichloroethylene a lot out here. It was like thousands of gallons a month, and they would use a lot of it to like spray wash planes to get the oil off them. Would just go into the ground. Salina's water supply is taken out over here. The groundwater flows in this direction. There is significant groundwater contamination and soil contamination here, and also a very complex geology. Like if we look at this highway from the west side of that, it's dominated by low permeability soils that are mainly where diffusion would be important, but there are some permeable zones. And when you get to the east side, it's dominantly high permeability materials. But in trying to clean up the chemicals in this area, it's very important to understand that diffusion is a big component. It's a long-term cleanup because you have to get the chemicals out of the low permeability material. So we're working on characterizing that now, and we're going to come up with a remedial plan in 1 or 2 years. This next site is a gas station in Goshen, Indiana, and it was owned for a number of years by a small chain of gas stations, Indiana-based. And then after that, it was bought by a large national firm, a huge national corporation. Both operators had releases, and the gasoline and free product moved from the tanks and the dispensers in a westward direction under this residential area. And at this site, the question was who was responsible and how much were they responsible for. And it was a court case that I was involved in, and we represented the first owners, and the second owners had an expert who was an expert in contaminant fate and transport. And I think really the key here was that person, that expert, came up with a chemical that was in the gasoline of the second owner that was not found at a well out here. And that way, in that sense, the second owner of the gas station said that they couldn't be responsible for any of this contamination out here. But what it turned out was that chemical, which I call an esoteric chemical, it's not very common, only could move just a little bit each year. And there's no way, even if it was released hundreds of years earlier, could it reach here. So it wasn't a really good argument. They didn't understand the concept of retardation. This is a site where the plant has been removed now, but they used to make automotive chassis, and all of this area in here, this is in southeastern Michigan, was a series of lagoons where they treated oily water. Eventually they got a treatment plant that was down here, and they could get rid of the lagoons, and as part of that they drained the lagoons, took out the oil, they built a test track on top. What happened was the weight of the test track, which was banked, squeezed out oil into a drainage ditch on this area, and they had to restart the investigation. The whole problem here in terms of the understanding of the site was the geology was about 4 or 5 feet of sand with a little bit of water, groundwater in it, over like 80 feet of clay. And every one of the wells that they had put in at this site were screened or too deep and never indicated where the oil was. And it also turned out that if they really looked closely, they would find that they way over-engineered the remediation. There really wasn't a large area where the oil came out but their remediation method didn't reflect that. So this was a case of not understanding light non-aqueous phase liquids. And finally, this is a case that recently was in court with, this is a concrete company that had gas tanks for many decades. This is a real retail operation. The retail operation found free product gasoline over here. After a number of investigations, trying to figure out where the gasoline came from, it was my opinion it came from here, and eventually the courts agreed with that. But what was interesting about this was the gasoline looked fresh. It was unweathered, largely unweathered, but it also had lead in it, which indicated that it was relatively old. So a big part of this case was understanding what kind of conditions allow gasoline to degrade versus those that don't. So a few takeaways from this, hopefully. I know we went through it fairly quickly. Different chemicals behave differently in the ground. The site investigation strategy, you must, for that, you must consider the chemical fate and transport, meaning your design of your wells, how deep your screens are, where you put them aerially. You need to understand what the chemical is doing, or expect what the chemical will do. And then, as we'll see in the next webinar, the chemical fate and transport is a key part of the site conceptual model. Often people just think about the physical framework of the geology and the hydrogeology, but you have to understand the chemicals as well. So our next seminar is March 12th, same time next Thursday. And I just wanted to let you know that if you're interested in having us look at any sites, we do a peer review. And a lot of our projects where we've found solutions where people couldn't find solutions before start with a peer review. And thank you. I'm going to take you off mute, and we can spend a little time. If anybody's got questions, we can talk for a few minutes. Otherwise, thank you for attending. So anybody out there interested in a particular topic? Okay, anybody have questions? Okay, well, thank you for attending, and hopefully you take out a couple of nuggets from what we talked about today. Thanks.